Okay, so on to the second lecture on surface integrals, and here's what we sort of developed last time. That we developed this idea of trying to understand integrals of this form, where your ds corresponds to a tiny little surface element on a curved surface, on a potentially curved surface in R3, and you have some sort of function f of x, y, z, some scalar valued function in R3, and the difficulty that we understood last time was that, look, this is given in terms of three different variables, x, y, and z. And this, on the other hand, it's kind of different depending on where you take it in this space. So you got this three-dimensionality associated with this fact. It's not really three-dimensional, but things depend on the three-dimensional variables. But on the other hand, what you really need to do is a two-dimensional integral, because the surface is two dimensions. That's why there's two integral signs here, and that's a two-dimensional object. So the big difficulty we faced was how we can rewrite this in terms of something nice. And what we developed last time was that, well, the whole issue is to parameterize this surface, right? So you have, I don't know, some u equals constant curves, and then you have some v equals constant curves along this, so that each location on the surface is a point of intersection between a u equals constant curve and a v equals constant curve. And that means that you can use the parameters u and v, just two parameters because it's two-dimensional, the parameters u and v to locate a point on the surface. That means that the x coordinate at that point is a function of u and v, so is the y coordinate, and so is the z coordinate. So your general coordinate r as a function of u and v can be represented in this way. So the whole idea now is to rewrite this whole integral in terms of just these two parameters u and v, befitting the fact that what you have here is essentially a two-dimensional integral. So you want to write everything in terms of u and v, so that you can rewrite this whole thing in terms of a double integral, a standard double integral over u and v, right? So the big difficulty was this guy over here, and what we discovered last time was that we can write it in this particular way. So that's the major sort of theoretical advance that we discovered last time. You write it like this, and where these correspond to the derivatives. So r subscript u corresponds to the derivative of this general location with respect to u. And then you have this as well, and then what you do is, when you take this cross product, you get a vector. Of course, you take the norm of the vector, and because you're taking the norm of the vector, it actually doesn't matter which order you write this in, right? So you can write this as rv cross ru instead if you want. Yeah, it's negative what you get before, but because you're taking the norm, it doesn't really matter. So the point is that once you have this in place, you can write everything in terms of u and v. So what I want to do in this lecture is do a couple of examples related to this. Okay, let's do this example first, right? Use spherical polar coordinates and a surface integral to determine the surface area of a sphere of radius a. So this is something we all know the answer to, but just to illustrate how we can use this concept of a surface integral, and the theory that we've developed, let's just try to do this example, right? So, okay, so we have a sphere of radius a, so it's going to be something like this. So here's your S, it's a sphere of radius a. And how can we couch this problem in terms of a surface integral? Well, the area I can think of as well adding together all the tiny little areas, right? So if d capital S is a tiny little surface area element which lies on the sphere, what I need to do is I need to just add them all together. So I can put in a function which is just one. Yeah, so the function here is just one, so there's nothing much going on in relation to the function. So that's one. Okay, good. So once I have this in mind, what I realize is that, look, now what I need to do is I need to express this ds. It's essentially the question of expressing the ds and using this parameterization. So parameterization, I've said this before, it's just a coordinate system. That's all it is, right? It's just a coordinate system for the surface of interest, and because it's two-dimensional, in this case, you have two parameters, u and v. Well, we are given a hint here, use spherical polar coordinates. Okay, so let's remind ourselves about spherical polar coordinates. So the spherical polar coordinate convention that I'm using here is these three variables, rho, phi, and theta. So given a general point in R3, rho is the distance to the origin. Phi is the angle measured downwards from the positive z-axis. And what is theta? Well, theta is, well, you drop down a perpendicular from your point to the xy plane, and you draw this line here. Well, theta is the angle from the positive x-axis. Now, this particular convention for spherical polar coordinates is trying to be consistent with your standard polar coordinate representation in the xy plane, because the angle theta is exactly the polar coordinate representation when you use r theta coordinates in the xy plane. Yeah, so that's why this convention is being used. But you should bear in mind that there's another very popular convention which is used for spherical polar coordinates. So this is replaced with r, and unfortunately these two things are interchanged with each other. So this is theta and this is phi, right? So use whichever thing that you're comfortable with, but for the purposes of this, this is the convention that we're going to be using, right? So if you use this convention, then what can we say about the x, y, and z coordinates? Well, to find the x coordinate is easy enough. I take this and I project it to the z axis. That angle is theta, so that's going to give me rho cosine phi, is going to be my z coordinate. What about my x and y coordinates? Well, so if I project this down into the xy plane, then this distance here, right? So this distance here is going to be rho sine phi. Yeah. And then I take that and I project that to the x-axis. So I take rho sine phi and I have to multiply that by cosine theta. If I project that to the y-axis, I multiply by sine theta. Right. So that's my representation of these coordinates. Okay. So in this case, my rho has to be non-negative. Right, that's just a distance to the origin. And the way that I've got this here, phi has to be between 0 and pi, because I can start right up there, but I can go all the way down to the negative z-axis and I don't go any further. Theta is your standard polar coordinate, theta in the xy plane. So that goes from 0 to 2 pi. You can go all the way around and come back to the x-axis. So here's my standard way of polar coordinates, right? A general point over here. But in this case, what I'm interested in is a sphere of radius a. So if I confine my attention to a sphere of radius a, what I'm saying is that this rho here is going to be replaced by a. It's always a at every single point on my sphere, because my sphere is something which looks like that, right? So that's always going to be a. So what I've done here is I've put in an a wherever I see a rho over here, and in this case it's not rho greater than or equal to 0, is rho equals a. Yeah, so on the sphere I have these properties, and that tells me then that, okay, so these are the two things which are varying, right? Rho is a constant, so I have these two things which are varying. So here is my coordinate system for the sphere, and this is my parameterization. So here are my two parameters, phi and theta, for the sphere. So this is going to play the role of my u and v. Okay, now I should just point out here that this parameterization for the sphere is something actually quite natural if we think of the globe, the Earth. If you're thinking of the Earth, so we think of latitude and longitude, right? So this thing here is actually the latitude, right? So, but it's measured in a slightly different way. It's measured from the North Pole, right? So the North Pole is 0. The equator is going to be pi over 2, and the South Pole is going to be pi according to this, right? The way that we normally do this, we would have this going from the way that we think of this on the Earth. We'll have this going from minus pi over 2 to pi over 2, right? So so minus pi over 2 would be the North Pole. So we think of this as minus 90 degrees, if you will, and the South Pole is plus 90 degrees. That's 90 degrees south, and the equator is 0. Okay, and similarly, this is the longitude. Right, so the way that we are thinking about this here in terms of spherical polar coordinates is that you go from 0 to 2 pi, you go all the way around. If you think of this on the surface of the Earth, we would not go from 0 to 2 pi. We have a 0 at the Greenwich meridian, and then we'll go to positive 180 degrees, which is positive pi, which is east, and then you go to negative 180 degrees, which is negative pi, which is west, right? So it's just the longitude and latitude that we use on the Earth is just a slight shift of this coordinate system. But anyway, so coming back to this, right? So we are going to be using this particular convention of coordinates, and here are our conditions, right? So as phi and theta vary across these domains, we are going to trace out the entire sphere, right? So every single point on the sphere can be defined in terms of these coordinates over here, and rho is always equal to a, right? So here is my parameterization there. I got x as a function of phi and theta, and also y and z. So that tells me that I can then write my r, which is a general coordinate on my surface of interest, in this case a sphere. It's going to be the x coordinate times I plus the y coordinate times j plus the z coordinate times k. And I've just this is just a rewriting of these three things in one term here. And why am I doing this? Well, the whole idea is that I want to find this ds, this surface area element ds, and that's given by taking these appropriate partial derivatives and then doing this calculation over here, and then I can convert into phi and theta. So what I've done in the first line here is I've rewritten what I had on the previous previous page. So there's my general location R represented in parametric form. So now what I need to do is I need to calculate this in order to figure out what my surface area element is. So let me just go ahead and do the calculations, right? So first, let me take the derivative of this with respect to phi. So there's a phi over here. So when I take the derivative, I'm going to get a cosine phi, and then the a and the cosine theta just come along because it's a partial derivative that I'm talking about. So over here, I'm going to get another cosine phi. When I take the derivative of this, I'm going to get negative sine phi. Okay, so that's taking the phi derivative, but I also need the theta derivative, right? So, okay, so let's take the theta derivative as well, partial derivative. So I got a cosine theta that's going to give me negative sine theta. And I've got a sine theta over here that's going to give me positive cosine theta. And this last term has no theta at all. So I don't have to write down anything. There's no k term. Okay, so I've calculated these two partial derivatives. Now what I need to do next is I need to calculate this this cross product. So we all know how to calculate the cross product. So we just write it in this form. So I got ij and k in the top row. And here's my first vector in the second row and my second vector in the last row. So I need to do this calculation. Okay, I'm going to keep this last part here and I'm going to erase the top and work it out. So let's see. So when I do this calculation, so the I component is going to be, well, that minus that. So this gives me 0. This gives me, well, I got a negative sign, but then I'm doing a minus, so the signs go away. So I'm going to get a squared sine squared phi cosine theta. A squared sine squared phi cosine theta. Fine. Let's look at the j component. So in the j component, what I need to do is need to take that times that, two negative signs. So that gives me a squared sine squared phi sine theta. Right. So that times that minus this times this, but I got a 0. So I just get a 0 over there. And finally, I need the k component. And for the k component, I need this. So this product gives me a squared sine phi cosine phi and cosine squared theta. There's two cosine thetas there. So that minus this. And when I'm doing the subtraction, I've got another negative sign, so that becomes a positive. And then what I see is that what I get is a squared sine phi cosine phi and sine squared theta. Okay, so I'm down to this point, right? So let's see whether we can simplify this a bit. So if I look at this carefully, I see that that's a 0 and that's a 0, right? So I've got an a squared sine squared phi there, a squared sine squared phi there. And over here, I've got a squared sine phi and a squared sine phi. So I see that I can pull out an a squared sine phi from everything inside. I just pull that completely out. And then I've got a sine phi, an extra sine phi remaining here. So I'm going to get sine phi cosine theta there. Once again, I got a sine phi remaining here. So I'm going to get sine phi sine theta there. And I pulled all of this stuff out. So I've got cosine phi cosine squared theta plus cosine phi sine squared theta. Okay, so I got this plus that. If I factor out a cosine phi from that, I'm going to get cosine squared theta plus sine squared theta, which I know is 1. So I'm just down to cosine phi. Okay, so it looks as if this is simplifying. Okay, it's still not completely simplified, but it's got this status over here. Okay, but what I really need is I need to find the norm of this. Yeah, so that's what I really need to do. So to find the norm of this, well, it's the length essentially of this vector here. So I'm just going to pull this stuff out straight out like that when I'm calculating the norm. A little thing to be slightly worried about is whether this is negative. A norm cannot be negative, of course, but this is not negative within the domain of interest because phi is between 0 and pi. So this is always positive, so that's fine. So this I can just think of as a prefactor. And then what I need to do is I need to calculate the length of this, the norm of this. So I just, sum of the squares basically of each of the components. So sine squared phi cosine squared theta from the first term, sine squared phi sine squared theta from the second term, and cosine squared phi from the third term. And once again, something nice happens, because if I factor out the sine squared phi from these first two terms, I'm going to get cosine squared theta plus sine squared theta, which is 1. Yeah. So these two terms together, it's just sine squared phi. Okay. But then what do I have? I have sine squared phi plus cosine squared phi. That's 1 as well. So everything inside the square root just becomes 1. So I'm left with a squared sine phi. So that's pretty nice. So the norm of this cross product between these two partial derivatives is a squared sine phi. So let me now, the whole aim of this was to write down this surface area element. And so what I've discovered here is that this is a squared sine phi. Right. So So ds is equal to that. Okay, so now we're in a great position to actually go ahead and do the calculation that we wanted. The area of the sphere was the integral of all the ds's, adding together all the ds's, if you will, with the function 1. But doing what we've done, we can rewrite all of this in terms of our parameters, in this case phi and theta, right? So ds we figured out is that, right? So let me just write that down, and then what I need to do is I need to put up the appropriate limits to span the sphere. So remember our convention, right? So it's sort of like parentheses. So the theta limits are from 0 to 2 pi. That's sort of the longitude, if you will, and the phi limits are from 0 to pi. That's the latitude, right? So this is the integral that I need to do. Now, when doing this integral, something which is very nice is that all the limits are constant, so we can do all sorts of nice things here. So one thing I can do is I can pull the a square all the way out. So I pull that out. Okay, and normally when we do an iterated integral, we work our way outwards from the inside. So you try to do this phi integral first, but I noticed that once I pulled out the a squared, when I look at this phi integral, it's the integral from 0 to pi of sine phi d phi. There is no theta dependence in this at all. Yeah, because there's no theta dependence in this, I can pull that entire term all the way out through the theta integral. Yeah? And that's what I've done here. Okay, what's remaining inside the theta integral is just that. It's 0 to 2 pi. So basically you can reduce this to a product of integrals, because we have this very nice structure in this case. And now this is of course trivial to do. So this integral is negative cosine phi from 0 to pi. This integral is, well, it's just 2 pi because I'm integrating the function 1. And what happens over here? So cosine phi, cosine pi is -1, cosine 0 is 1. So with the negative sign and so on, this whole term contributes a factor of 2. So then I've got a 2 pi plus a factor of 2 plus a squared. It's 4 pi a squared, which we know is correct. Okay, so that's one simple example using this idea. Let's do another example where we're trying to calculate. In this case, we're trying to calculate an integral z ds. Okay, so now we actually have a function here where s is the surface of the half cylinder. Oh, what does that mean? Half cylinder x squared plus y squared equals a squared. Well, what is this part? Well, in the xy plane, that's just a circle of radius a, but you get exactly the same circle of radius a in every single z equals constant plane. So this is just a cylinder. So this part here corresponds to the yellow surface that I have here. It's just a cylinder which extends up. But I have a condition here, x is greater than or equal to 0. So if I'm looking at that, so here's my x-axis coming in that direction, x is greater than or equal to 0. So here's my y-axis, so it's everything to the right of the y-axis, right? So what I've indicated here in green is sort of essentially what's along the y-axis. So I slice off the back of this. So it's only the front part of the cylinder. So it's only this part that we're interested in. It's the front part because of that. And then there's another condition here, z is between 0 and 1, right? So here's a z equals 0 plane, here's a z equals 1 plane. So it's this part, well, it's this part of the cylinder that we need, right? Okay, so we have to do the integral over this part of the cylinder. Now, the big issue here is, of course, how you rewrite this in terms of a parametric variable. Now, if given a general surface, trying to figure out a good parameterization for it is actually quite hard. But for fairly straightforward surfaces, like spheres and cylinders and so on, it's quite easy, because we just use our understanding of different coordinate systems. So in this case, essentially using cylindrical polar coordinates seems to be the way to go, because you've got a cylinder. Right? And it actually becomes even easier because it's a cylinder of constant radius a. So in this case, I can think of doing the cylindrical parameterization. So I'm thinking of cylindrical polar coordinates, which is r theta z, right? Little r theta z, where little r and theta. So r theta z, right? Where little r and theta are just the polar coordinates in the plane, but that r is always equal to a. Yeah, so there's nothing to worry about. So that gives me that the x coordinate is a cosine theta, the y coordinate is a sine theta, and the z coordinate is just z, right? It's in general z. So here's the cylindrical parameterization, if you will, for this surface here. Now, for this example, I'm just going to use this alternative notation. I could have written this as a cosine theta I plus a sine theta j plus zk, but I'm just writing this now in component form, right? Just for variety, because we need to be comfortable with all of these different approaches. Okay, so now, so these are my parameters, then theta and z. So what are my conditions? Well, the z1 is easy. Z is between 0 and 1, and theta is the polar coordinate theta, so that's the angle measured from the positive x-axis. So I have to go in that direction. So this goes all the way up to up to pi over 2 in this case. So it's between 0 and pi over 2. And then, well, what is this? So this part is between, well, if I go all the way around, I have to then think of, something, going up to 2 pi, right? 3 pi over 2 to 2 pi or something like that. So I have to break it up into two discontinuous portions, and that's not really nice. It's much easier if you think of this in this continuous sense. So you go from minus pi over 2, right? So negative corresponds to the fact that you're going in the wrong direction. So negative pi over 2 is a negative y-axis. 0 is the x-axis, and pi over 2 is the y-axis. So you go from negative pi over 2 to pi over 2. So here are my conditions now on my parameters, the parameterization. So all right, so now I know what to do. So I've got this, and now what I need to do is, I mean, the most difficult part is trying to figure out what that is in terms of theta and z, which are my two parameters. So what do we do? So I write down r. So that's what I have, and here's what I need, right? So here's what I need. So my ds is given by this quantity over here. So this tells me that I need to take the theta derivative and the z derivative. So I've put everything down quite quickly over here because this is now fairly easy for us, I think. So when I take the theta derivative of this, so cosine theta gives me negative sine theta, sine theta gives me cosine theta, and there's no theta term over here, so that's just a 0. Yeah. On the other hand, the z derivative, when I take the z derivative, that's even easier. There's no z in the first term, no z in the second term, and there's a 1 in the third term. So that's that. So, okay, so now let me take the cross product between these two, and it's given by this thing over here. So when I calculate the cross product, what do I get? So my I term is going to be, well, it's going to be this minus that. The second term is just 0. So what I get is a cosine theta. And then I have my j term. So what happens in my j term? I have to take that times that, which is 0, minus this times that. So the minus sign and that negative sign cancel. So I'm just going to get a sine theta. So that's easy. So a sine theta. And then I have a k component. So what's my k component going to be? My k component, so here's k. So my k component is that, which is 0, minus that, which is also 0. So there's no k component. So this is actually quite nice. So what I can see here is that when I take this cross product, I get a cosine theta and a sine theta are my components, and 0 are my components. Okay, but what I really need is I need the norm of this. So it's going to be the length of this. So it's going to be this thing squared plus this thing squared plus 0 squared. Okay, so that's easy enough to do. So a squared cosine squared theta plus a squared sine squared theta plus 0 squared, d theta dz is what I get. And if I factor out the a squared here, I get cosine squared plus sine squared, which is 1. Pull the a squared out of the square root. A is a positive quantity, so that's just going to be a. Okay, so this is it, right? So your area element on the cylindrical surface is given by this, and we can actually visualize this in other ways as well, because a d theta is what you get when you so you have your x and y axis. So if you change theta by a small amount, you're going to generate an a d theta in this direction. You change z by a small amount, you're going to generate a z in that direction. Anyway, so that's your area element. Okay, now we're in a position to go ahead and do the calculation that we need to do. So what do we need to do? So this is what we were asked to do. So the z here, we have to rewrite this function in terms of the parameterization that I had, but the parameterization was actually theta and z. So I can just keep the z as it is because z is z, right? So it's part of the parameterization. And then I need to put in the appropriate limits. So the z limits are going from 0 to 1, and the theta limits we've argued go from negative pi over 2 to pi over 2. So here's what we need to do, and we can do this quite quickly. So once again, taking advantage of the fact that all the limits that you see there are constant, I first pull out the a, and then what I can see is that so I have my inner integral. Then I pulled out the a. I can pull the z out of this inner integral as well because I'm integrating with respect to theta. And then what I'm just left with is just d theta, right? So both of these terms are gone. Just d theta from negative pi to pi over 2. And then I pull all of that all the way out of this external integral. So what I'm left with then is negative pi over 2 to pi over 2 d theta is what happens when I pull that out. What remains? Well, this z, I pulled it out of this limit, but I can't pull it out of the second limit because that's integrating with respect to z. So I've got a z which is hanging out here, and so that's just an integral from 0 to 1 of z dz. So once again, you're able to just factor this out into a couple of different integrals in this case because of the structure of this. So what do I get? I get a for the first term. For the second term, it's just integrating the function 1 from negative pi over 2 to pi over 2. So I'm just going to get a factor of pi there. And the last term, so this is z squared over 2 from 0 to 1. So it's going to be 1/2. Right? So that's going to be 1/2. So here's my answer. It's pi a over 2. Right? So that's how you can do an integral given a parameterization. Of course, finding a parameterization for some random surface is incredibly difficult, but once you do have a parameterization, the key thing is this thing here. So that's the difficult thing to typically that you need to try to do. You write everything in terms of a double integral with respect to the two parameters, and then you just convert it into a double integral and do the double integral, right, in whichever way works. Okay, so the next lecture is going to talk about a slightly different form of surface integral, something called a flux integral, which is quite interesting and very, very important in fluid mechanics and electromagnetics.